Okay, now let's look at some examples of saddle point problems. The first example is the stationary Stokes equation. Now, for the Stokes equation, we have one unknown, which is a vector field u, and the scalar field p. And the given data is the right-hand side f, which is a vector field. And let's say we have this strictly boundary condition on the boundary. And let's say, well, okay, so we have omega, right? Omega, let's say, nice bounded domain. Okay. And now we can write this in variational form. U is going to be, since U has this homogeneous Dirichlet boundary condition, U would correspond to this space H10 with vector values. And for the P, by the way, U corresponds to the velocity field of a fluid, and P corresponds to the pressure. So the pressure space is going to be L2 with zero mean. Okay, zero mean means just that the integral over omega of the pressure is equal to 0. It's because you can see that in the equation pressure only enters through the gradient, so adding constants are not going to change the equation. So we write the Stokes equation in variational form. Now here you can see that we did integration by parts, and well, that's why we have this minus sign. Here also we had integration by parts. There are no boundary terms because of the Dirichlet boundary condition. And for the second equation we did not perform any integration by parts, basically because we will need, here we have by integration by parts, right? We're going to have one derivative on u anyway, so we just leave it as it is. Now, if we want to compare this to the general framework that we saw in the last lesson, the operator A is going to be the minus Laplacian, that would correspond to this term here, and B is minus divergence, which corresponds to this term, and B prime is the gradient, so that would correspond to that term. Okay, so remember the gradient, this B prime is acting on P, and if you look at this term, or we can also just look here, when you integrate by parts, this divergence will go to the other side to become gradient, and this minus sign will become plus. Okay, so what do we need to check? We need to check A0, that is basically the restriction of A onto the kernel of B. Now, what is the kernel of B? The kernel of B would be, because B is divergence-free vector fields that are in this space. Okay, so we need to show that the A0 is invertible. Basically, the Laplacian in divergence-free space is invertible, and we need to show that B prime or gradient is bounded below. But we can see that this bilinear form is actually strictly coercive on the whole space H10. So we don't, without even restricting it to the kernel of B, we see that this is already strictly coercive. That means, of course, it is strictly coercive on the subspace. So kernel of B is the divergence-free space here. So it is invertible immediately. So that means the only condition we need to check is the bounded below condition for the gradient, or B prime. Okay, so that can be written in terms of the inf subcondition in this way. So we basically going to construct, so what this condition says is that given Q from the pressure space, basically it says that there exists some V that gives you this inequality, right? So suppose we have Q in L2, then what we're going to do is we're going to solve this Neumann problem, okay? Because omega is assumed to be nice, we can solve this Neumann problem. And then by using that solution phi, we're going to construct that V by this formula. So you simply take the gradient. Okay. Now, because omega is nice, we have elliptic regularity that tells us that phi, the solution of this Neumann problem, is in H2. Here are some minimal conditions. It would be enough to assume that omega is C11 or convex. So if phi is in H2, then V will be in H1 because of this formula here. And now this Neumann condition becomes, in terms of V, just the condition that the normal component of V is equal to 0 on the boundary. So basically, normal component of, let's say this is the boundary of omega, normal component of V 0 means that V is going to be basically tangential to omega, right? So let's say this is vector field V. Okay, so let's bound the H1 norm of V. Now H1 norm of V is bounded by the H2 norm of phi, and that's bounded by the L2 norm of Q by elliptic regularity. So now we look at this expression at the top here and simply substitute V equal to the gradient of phi, so that would be Q against the Laplacian of phi, and the Laplacian of phi is equal to Q. So if we substitute that, we simply have the L2 norm squared of Q. And we use here this inequality once, that gives us, that's bounded from below by the H1 norm of V times the L2 norm of Q. So if you substitute this expression into here, what we get? We get H1 norm of V, L2 norm of Q divided by H1 norm of V. So here they cancel, and that's the L2 norm of Q. That's what we wanted here. So that gives us the if-sub condition for B prime, actually. But what do we need? So let's actually see what is here. Right here, V is actually in V, right? And what is this space V? V is actually V is just H1 vector fields with 0 boundary condition. What we have is we only have now normal component V is equal to 0. So the idea now is to modify this V, okay, V that we found, by some divergence free vector field, so that we would not have any effect in this argument, to make the boundary condition 0. Okay. So we're going to just restrict ourselves to the two-dimensional case and show that it can actually, the tangential components can actually make 0. Okay, in order to construct a divergence-free vector field W, okay, first we're going to construct a scalar function psi in H2, satisfying this on the boundary. So it will satisfy the Dirichlet boundary condition, and the normal derivative will satisfy this condition. So the normal derivative is equal to the tangential component of our vector field V. This is an extension problem, and it can be solved, and we can construct psi satisfying this estimate. Okay, supposing that we constructed this psi, we define W to be the curl of psi in 2 dimensions. Now psi is a scalar field, and the curl is going to be a vector field defined by this expression, which is simply the 90-degree rotated gradient of psi. Now divergence of W will be 0 by construction. Basically, just look at this formula here. And now let's look at the normal component of W on the boundary of omega. The normal component of W is the normal unit normal vector field nu dotted against the curl of psi, which is equal to, because the curl is 90-degree rotated gradient, the tangential vector normal tangential unit tangential vector field T dotted with the gradient of psi. Okay, but the psi is 0 on the boundary. That means the tangential component of the gradient of psi is 0. Now let's look at the tangential component of W. Again, tangential unit vector dotted with curl. By the same reason, it will be equal to the minus the unit normal dotted with the gradient, and this is just the normal derivative of psi, which is by construction equal to V dotted with T, or the tangential component of V. So we're going to we modify now our V by adding W to it. So V bar will be now our new test function. And by construction, we can see that V bar is actually 0 on the boundary of omega. And because W is divergence free, this expression that is in the denominator of or numerator of the inf subcondition for B prime, it doesn't change, so we have the inf subcondition. So this shows the well-posedness of the stationary Stokes equation in 2 dimensions on nice domains. Okay, our next example is Poisson problem. So it's a different formulation of the Poisson problem. So the original, our problem is this. Okay, we have homogeneous Dirichlet boundary condition, and we're going to write this as a system of equations by introducing this vector field sigma. So if sigma is the divergence of U, the gradient of U, then the first equation becomes divergence of sigma is equal to F. I think we are missing minus sign here. And this second equation is just a definition of sigma. So we have this system of equations. So if we just look at this system and try to write in a variational form, so let's start with the second equation, test it against a vector field tau. Okay, test this against the vector field tau and do one integration by parts. So over here we did integration by parts. The derivative from U now the derivative is on tau, and the space for tau and sigma is going to be this space called H div, which is simply the space of L2 vector fields whose divergence is in L2, because here we see that we only need to take the divergence of tau. For the first equation here, we just simply test it against a scalar function V. Okay, and there is no integration by parts. So the space for V, that is this space Q, will be just an L2 space. Again, note that there's only divergence of sigma is involved here, and there's divergence of tau. There's no any other derivative on sigma or tau. So now we can see here the operator A should be around here, right? So the operator A is actually just the identity operator, and we can see that B prime is minus divergence. B prime is here. Now let's look at what happens to the boundary condition. So I claim that actually the boundary condition will arise naturally without us imposing anything. So we are looking at the first equation. You do integration by parts over here. So that gives us this term in the volume and this term on the boundary. Okay. Now you look at these two terms and combine them. Test against tau vector fields that are 0 on the boundary. If you do that, this term will disappear and just these two integrals will give us sigma is equal to the gradient of u in the domain. Okay, so because of that, for all test functions tau, this will basically disappear. And now we consider test functions tau, test vector fields tau that are non-zero on the boundary, and that give us, because this combination can be something arbitrary, this gives us u equal to 0 on the boundary. So the Dirichlet boundary condition actually arises naturally in this formulation. By the way, this type of formulations are called mixed formulations. Now we want to check, what do we need to check in order to prove that this formulation is well posed? First, we need to show that A0 is invertible, and second, we need to have B prime bounded below. So let's look at A0 first. So we have A here. Similarly to what happened to the Stokes equation, this looks very much positive, right? So let's look at this. Now, to show positivity or coercivity, we just check what is A tau. But remember, in order to show coercivity, what is the space in which tau lives? It's H div, it's not L2. If it was L2, this would have been enough to show strict coercivity. But because there is this divergence-free condition, divergence in L2 condition is involved, in the norm of V, we also have the divergence term. So this would be the norm squared of tau in the H div space. But we can add this term just for free because B is actually, so B prime is gradient and B is equal to divergence. So the kernel of B is divergence free space. So in the divergence free space, we can just add this term for free. So in the divergence free space, the L2 norm of tau is equal to the V norm of tau. So we have a strictly coercive on not V, but it is on the divergence free space, or the kernel of B. That's what we want. Okay. So here is an interesting situation where for the Stokes problem, this A was actually strictly coercive on the whole space without even restricting to this kernel of B. But in this situation, we really need to restrict, otherwise this is not coercive. So it's only strictly coercive when when we restrict ourselves to the divergence-free space. Okay, so the next condition is to check the if subcondition for B prime. What is our B prime? That's the B prime is gradient, and this is what we want to check. It's exactly the same as the Stokes problem. So now again, the meaning of this is, given V, we need to construct tau that has some nice properties like this. So what we want to do is we want to solve, given V, we want to solve this Poisson problem with zero Dirichlet boundary condition. Then we simply put tau equal to the gradient of Z. Okay. Remember, for the Stokes case, we solve with some type of Neumann condition, but here we are solving it with the Dirichlet boundary condition. Okay, so tau is this. We want to compute the divergence of tau. If you compute divergence, it is the Laplacian of Z, and that is equal to V. And we can evaluate the L2 norm of divergence of tau, and that would be just the L2 norm of V. And in the V norm of tau, we also need to compute the L2 norm of tau. And the L2 norm of tau would be bounded by the H1 norm of Z, just by the definition. And H1 norm of Z is bounded by the L2 norm of V by elliptic regularity. So summing up these two estimates, we see that the V norm of tau is bounded by the Q norm of V. And that would be enough. So look at the numerator, and because this is divergence of tau, which is equal to V, it just becomes the L2 norm squared of V. And then we use this estimate that gives us, that's bounded from below by tau times V. And that's enough to give us this if subcondition for B prime. So that now proves that the mixed formulation of the Poisson equation with homogeneous Dirichlet boundary condition is well posed.